École nationale supérieure de techniques avancées, Bretagne, Brest, France. In 2002, we created in France the working group Set Computation, about 400 researchers. This research and new results in the interval methods and their applications to nonlinear control, nonlinear stability, and simultaneous localization and mapping are worldwide recognized. And we will hold here at EEE School a 3-day series of lectures with workshops. So today, tomorrow, and Wednesday. Thank you very much for accepting my invitation.
Thank you very much for the introduction. So I will present you for this lessons interval robotics. So I call it interval robotics because it's very similar to what influenced by the book probabilistic robotics. So I mean, what we are doing is robotics, but we try to use as much as possible interval analysis, and I will try to explain you why it is important and why we can do with intervals that cannot be done without intervals. So it is the objective of the lesson. So what happened today, I will introduce, maybe for 1 hour, the mathematical concept, but I will go quite slowly. If I go too slowly, please tell it to me. If I go too fast, the same. So you can interrupt me to ask me questions at any moment. So I will introduce interval computation first. Then I will show you today some application to bounded error estimation or to solving nonlinear problems. And then slowly I will come to the applications. So by application, I show you on some videos before what I mean by application. So in Brest, it's in Brittany in France, west part of France. There we have financial support to develop ocean robotics. So by ocean robotics, I mean underwater robots, swarm of underwater robots, and also sailboat robots. I showed before some videos on sailboat robots. Everything is done in Brest. So first, I will first introduce some notation, so a few minutes, related to set theory. So I will show you a few slides. So I will not define the intersection, union, and so on, but I will directly go to what I call by a direct image. So imagine I have a function from Rn to Rp, for instance. What I call the direct image, so f is the mapping from a set to another, it's the set of all f of x, such x belongs to the initial set. Quite classical, and I will use this notation later. The reciprocal image is the set of all x that are mapped inside y. So I prefer to recall it because I will need it. It was a small exercise, so I will solve it now. If I have a mapping f, so the image of A, for instance, I will just take the first one. F of A will be, for instance, 2 and 3. So, as explained here. The reciprocal image of B is a set of all points that are mapped into B. So here, of course, it will be A, B, C, E. So these notations are quite classical, and if it is not, please tell it to me. For now, I come to intervals, and I will try to apply this definition. Consider the mapping f x squared. So I take an interval. What is an interval for me? An interval is a connected subset of R, which is closed. I mean, I will not consider open bounds, only closed bounds. So the image by f of the interval 2, 3 will be, of course, 4, 9. But the reciprocal image of 4, 9 will be the union of two intervals, the following intervals. Okay. So, since I want to deal with interval analysis, I want only to deal with intervals, I will, most of the time, I don't like the union of intervals, I will take the smallest interval, which encloses the union of interval I consider. Not at the moment, but we'll see later. Okay, I will not speak about relation, so please don't look at this. I will come directly to interval arithmetic. So what is interval arithmetic? It's some kind of extension of all operations we have on real numbers. For instance, so an interval for us will be, for instance, a random variable which belongs in an interval and will represent by the interval itself. So how can I extend all operations I have on intervals or on real numbers to intervals? So I will define as follows. I take a binary operation, plus, minus, multiplication, and so on, max and min, are also binary operators. Then I take the set of all x operator y, such as x and y belongs to the previous to their domain. So domain or interval, I will employ both. So what is a domain? It's a set which encloses the random variable. So I take all possibilities for x operator y. Then this set, here and here, this set, may not be an interval. So it can be the union of two intervals if, for instance, this operator is not continuous. So I have a second operator, this one and this one, which takes the smallest interval, which encloses all possibilities for x operator y. Understand? So, how can I add two intervals? Of course, I think in that way, if A belongs to this interval, if B belongs to this interval, A plus B belongs to which interval? Please tell it to me.
1, 8.
Yeah, perfect. So, 1, 8. The second one is a multiplication. So, if A belongs to that, B belongs to this interval, what about A times B? Minus 2. Are you sure?
Minus 5.
Minus
Minus
5.
5. Minus 5.
Minus 5 is possible.
15.
Can I go further to the left? No, minus 5 is possible because if A equals minus 1, B is 5, I reach minus 5. So it's important to understand. So here, this interval contains all possibilities for A times B if A belongs to this and B to this. It's also possible for division, and I apply this definition. Okay? So this is the way I will extend to intervals binary operators I had for real numbers. Important to understand. Also, you should understand that all these operations should be guaranteed. I mean, in the computer, these operations are floating point operations. So I need to have outward rounding of the result to be sure that I will not lose a feasible value for the product. Understand? So I need some outward rounding. I will not enter in these details here. But the idea is to prove some properties of dynamic system. If I want to validate proof, I need outward rounding. And using interval analysis, it has been able to prove some conjecture, like the Lorentz conjecture or the Kepler conjecture, have been proved using interval analysis. So if I want to guarantee some properties, I need outward rounding. Okay? So of course, if I have two intervals, I can multiply. I have some operator multiplies and so on, only taking into account the bounds. Okay, so this is min, this is max. So if I want to multiply, okay, for multiplication, I take the min, I take the max, and I obtain all possibilities. Okay? I have explained how to extend binary operators to intervals. Now, what about function, classical function from R to R? How can I define it? I take all possibilities for f of x, and I take the smallest interval containing this set. For instance, so you should understand, for instance, sinus 0p is 0, 1, of course. So now something, maybe a square is, what is the square of minus 1, 3? Will be
1, 9.
not 1,
0, 9.
0, 9. So you should understand that when I develop the square, I have to think about all possibilities. The absolute value of minus 7, 1? 0, 7, good. Now more complicated. Square root of minus 10, 4. So I have to apply this definition. And to apply this definition, I need the image of f of x. So I take all possibilities of the square root, and I will obtain 0, 2. Logarithm of minus 2, minus 1, I will obtain the empty set. So the empty set is an interval. R, so the set of all real numbers, is also an interval, because it is a connected subset of R, and empty set and R are also closed. So there are intervals. So intersection between two intervals are intervals also. Okay? That's all you need to know about interval computation, but you need to understand. Let me continue about boxes. So I will introduce boxes. It's quite easy also. X, a box, is a Cartesian product of n intervals. The set of all boxes will be denoted like this. So most of the time, I like interval of Rn. So of course, I can do intervals of a lot of things. If I have a set, for instance, Rn, which is a lattice, so with order structure, then I can define interval of such sets. So let me show what is an interval. It is a square. Oh, I need this picture. Okay, I want this picture. So here I have the Cartesian of this product of, I make the Cartesian product of this interval, this interval, this interval, and I obtain a box. The width of a box is the, of course, the length of the largest side. Okay, so it can be, for instance, here, this plate. No, excuse me. The width can be, for instance, this length. Okay, it's a box. It's important for not now, maybe later. I will come. So why interval analysis is important for us? Because it makes it possible to compute inclusion function. If you have other tools to build inclusion function, then you can replace interval analysis by your new tool. So what is an inclusion function? First of all, let me explain here on the board. If I have here, well, R, for instance, R2. Here, I have another set. So it can be, for instance, Rn, and here it can be Rm. If I take a point, then this point will be mapped by a function f into another point, because it's a function. If now I take a box, this is a box, then this point will be mapped here, and so on, and the image of a box might be something like this. If the function is continuous, it might be like this, but it can be with two disconnected components. Now, this is almost impossible to compute for any function f. So what is an inclusion function? An inclusion function, you have the box x. Here, it is f of x, the image of x. Now, if I take I want a bigger box. I will call it f of x. To a box, I think, so it is mapped into a bigger box, which encloses all possibility for f of x. It is what I will call an inclusion function. So I will give you here the definition. For all box x, the inclusion function will give me a box which encloses the image by f of this box. If I have this inclusion, then I will have an inclusion function. Of course, I can have the optimal one is a smaller one, but most of the time I will be able to compute an inclusion function with some pessimism. The pessimism is this. Okay. So why this definition is important? Because, as you will see, with interval computation, we are able to compute inclusion function for very large class of nonlinear function f. Moreover, they will have some nice properties. So what I mean by nice properties? It is monotonic. So imagine I take this box and I inflate it. The image in blue will also be inflated. The inclusion function will be said to be monotonic if I inflate this one, then this box is also inflated. It is the first rule. It is said to be monotonic with respect to the inclusion. It is minimal if I take this one and I obtain the smallest one, as so in the previous slide. Minimal is difficult to compute. It is an NPR problem. So it will be difficult for us to find minimal inclusion function. It is thin if, imagine I take, instead of taking this box, I take a very, very small box. Small, it is a point. Its width is 0. Then the image of a point, if can be something bigger, if it encloses a true value. But most of the time, I will be able to find a thin inclusion function. I mean, if the width of x is 0, the image by the inclusion function will also be 0. The width, W means width. It is convergent. Convergent is also important. I take this box, and I will move it so that I will converge to a point. If the result here on the image space also converge to 0, then I will say that the inclusion function is convergent. So the good news with interval arithmetic is that we are able, for a very large class of functions, what I mean by a large class of function is all functions that can be expressed by a finite algorithm. It's a very with sine, cos, composition with loops, composition of classical functions. So I will be able to compute monotonic, thin, and convergent inclusion function easily. So,
it is a definition, or it is your principle.
what is
You have the minimum, the 0, and you have to find why fx is 0 and another is 0 as well.
so what is, so your question is?
Your question is back to your previous slide.
Yes?
The number 3, for example, row 3. If wx is 0, then you have another wfx of 0 as well. How
Yeah.
you can define this one?
I'm not sure I understand the question about thin or convergent. Thin. Thin. So if
It's the principle or it's your regulation have you already defined this one. In the future, you will use this one or you will not use it.
I'm sorry, I have some. So
That is the key issue.
so yeah, thin is easy. Thin is easy. If I take maybe I can come back to your question just after. I'm not sure I can, but we'll understand better just after. And an example. So this one is, as you can see, you have nested box on the right, nested image. Of course, it's always like this on the right, but the boxes of the inclusion function are not nested. So it is convergent, but not monotonic.
Sorry, I think you can revisit that. Just his question was, the property defined in the previous 4 properties, are you just giving as a definition? Say if the...
It's okay.
It's a definition.
It's a definition.
Yeah. Okay.
It is a definition.
Yeah.
It's not property. Now, what is important is that we show that very easily we will be able to compute functions that satisfy these properties, but they are defined as properties. Okay? Okay, so convergent and monotonic, nested on the right, nested on the left. So, I think now we can understand how it works. I have a function f of x squared plus 2. So this function, basically. Now I want to know what is a natural inclusion function. So I have not defined yet what is a natural, but I will try to do it now. So how can I do it? The idea is just to replace f of x and to consider this new function as this one. I take the square of x plus 2x plus 4. So I take the same expression, but I will evaluate using interval analysis. So to an interval, I will associate another interval. How can I compute it? I will compute as follows on an example. For instance, minus 3, 4 square plus 2 times minus 3, 4 plus 4. So this is computed. The result of this is 0, 16 plus minus 6, 8 plus 4, which is equal to minus 2
28.
28. Okay, this is the way. So, what you can understand is, if I compute the exact image here, the exact image, it is 328. So I have not computed the exact image. There is some pessimism here. Of course, I have the inclusion. And you should understand why I have the inclusion. Because at each step, this contains all possible values for x squared. This one contains all possibilities for 2 times x, and so on. So at each step, what I compute is an interval which includes the corresponding to the true value of the variable. So, you should understand why this interval contains all possible values. And here I have a simple function so that I can compute this image. But it can work even for any kind of function which results in a finite composition of classical elementary operation I have defined before. You can have sine, cos, plus, multiply, and so on. Okay? Also, this inclusion function is convergent. Why? Because it is the sum of convergent inclusion function. Since each elementary inclusion function is monotonic and is convergent, the sum, the composition, and so on will also be convergent and monotonic. So what I want to say is that I have x, which is here, minus this one. If I reduce it to a point, the result will also become a point. It will be convergent. So this is important to understand this example. Yes?
So I don't get the note, because you said this function is defined.
This is the exact image.
So the exact image is between 3 and 28?
No, the exact image, I can compute it because it's quadratic. So I can compute it exactly. That's why I have chosen a simple example like this one, because I can compute the exact image. It is 320. Now, what I have computed easily is not the exact image. It's a superset. It encloses the exact image. But you have some pessimism. This one is larger than this one. I would like to have this one, but most of the time I'm not able to compute it. This one I will always be able to compute it. Okay? So, let me give you another example. I have a function from R2 to R3. It is nonlinear function. I take the same expression and I replace it by intervals. All occurrences are replaced by corresponding intervals, and I will apply interval arithmetic. So it's well defined to a box. I obtain a box. It will be convergent, it will be monotonic, but it will also be minimal here. Why? Because you have a theorem from Moore, the one who created the interval analysis, which tells you that in each coordinate function, if you have on at most one occurrence of x1 or x2, as it is the case here, then if you apply the natural inclusion function, you will obtain the minimal one. It's a special case. Okay, most of the time it is never minimal. It's okay? Okay. Now I have an algorithm, a simulator of a robot or any kind of with loops and so on. I have the code, the C++ code of the function with 3 inputs, 2 outputs. I want to have an inclusion function of this algorithm. How can I do it? I do not have to program once more the algorithm. I just take the same algorithm and with overloading concepts, I will replace the inputs by intervals and all operation by the interval counterpart. And I obtain the same algorithm with intervals. If I apply this algorithm, I will obtain an inclusion function which is convergent, thin, and monotonic. You understand? So the natural inclusion function is easy to compute. It's not always the most efficient one, but just to show you that with interval analysis, you have a lot of methods that make you possible to compute inclusion function. It means that this algorithm will return 2 intervals, and these 2 intervals enclose all possibilities for the algorithm with the inputs inside the corresponding. Okay, it's okay? Tell me if I go too fast or too slow. You have other inclusion function. I have presented the simplest one, and I will not go further with that.
If your inclusion function is not minimal,
Yes.
does the order of computation make a difference?
So it is not minimal here, but it is convergent. I mean, if
What I'm thinking is you might have a different order in your code, which in the ordinary arithmetic makes no difference, but in your interval analysis does make a difference. Is that possible?
so if I change the order of the instruction without changing the result of the algorithm, it's what you mean, then I will obtain another inclusion function. Okay. But it will still be convergent and monotonic. I will not execute this inclusion function. Oops, sorry. I will go to maybe to Boolean interval. So what is a Boolean number? The Boolean number is 0 false. It's false, false, true. Okay. There is a relation. 0 is smaller than 0, of course. We can define that false is smaller than true. Then we have a lattice. So we can define lattice. I will not explain what is a lattice or the set. So I can define intervals. How many intervals I will have in B? Tell me how many intervals I can have in the set of Boolean numbers. 3. So you will have 0, 0, 1, 1, 0, 1. What else?
Do you consider 1, 0 different than 0, 1?
No. You will have also the empty set. The empty set is also an interval. Okay. Okay. So I can use intervals when I have to manipulate some conditional. I will maybe when I want to find union of sets. I will need it later. So what? So what is a Boolean interval arithmetic? So I take the same concept, I take the union of the intersection, I take all possibilities, and I am able to define the union, intersection, the complementary of or the negation of Boolean intervals. So I will not enter in it, except here I want to compute this. 0, 1, or 1 is this or.
0.
It's 1. Okay? Perhaps or sure is sure. It's true. Okay. 0, 1 and false and true is 0, 1. What is the global result? 0, 1. Okay. It's important when because sometimes I have if statement in the algorithm, so I will read later. So what? Okay, I think inclusion test. I will not speak about inclusion test now, and I think we have all that was I wanted to introduce to understand the basic notion of interval analysis. Now we'll enter in the algorithm. Yes, please?
And the Boolean analysis, I mean, the end result, you're getting to either 0 or 1.
Yes.
But the main reason why you're using Boolean is to figure out, is it 0 or 1?
Yes, yes, sometimes, of course, sometimes I want to obtain 1, sometimes 0, and that's true, that's true. So here, bad luck, I obtained 0, 1. Because it's possible to be 0, the result could be 1 also.
Oh.
Sometimes, of course, it's better to have 1 or 0.
Yeah.
But now we'll enter in the algorithms of interval analysis. Okay. Okay, so now what is important to start chapter 2? Everybody has to understand what is an inclusion function. Okay? And you should understand that it is easy to compute, that it is convergent and monotonic. You can start chapter 2. Chapter 2, first, subpadding. Subpadding, what is a subpadding? So, it's important to a little bit of mathematics. So, the set of subsets of Rn is can be equipped with order relation, the inclusion. A is included in B. It means A is smaller than B. It is an order relation. It is a lattice. It is a lattice because I have largest lower bound and highest upper bound, so I can define the minimum between A and B as the intersection, the supremum between A and B as the smallest set which includes A and B, supremum. It makes me a lattice. In lattice, I can define intervals. For instance, if A is here, if B is here, AB is an interval of sets. This set, X, belongs to this interval. This interval contains many sets. So intervals of sets are good to represent uncertain sets. Just a little bit of mathematics. I will come back to what is subpadding. So, inside the machine, it's difficult to represent sets because I have floating point numbers. So what can I do? If I have a set, for instance a set X, which is unknown, I can approximate by boxes. So I can take, for instance, boxes that are inside, but I can also approximate by boxes that are outside. Union of boxes made with floating point numbers will be X minus, for this one, is included in X, the unknown set, which is included into X plus. X plus is this one. As we can see, X is an element of the interval X minus X plus. Okay. So what is a subpathing? It's a union of non-overlapping boxes. With this concept, I will be able to approximate any uncertain set between two sets that can be memorized inside the machine. So let me show you an example. Let me take this ring. I want to represent inside the machine this ring. I can take inner subpathing, the white boxes, and another one I add the gray boxes, and I will obtain X minus X plus. And I can approximate, I can be as accurate as I want. I will need more memory, but I will be able to represent uncertain sets. Okay? So, of course, I would like to manipulate this set, because, for instance, this set can correspond to a position of a robot. If I measure the distance from this point with a given accuracy, I will know that the robot is inside this ring. So it's nice to represent information about the robot. Now I would like to intersect them, to add them, to compute the inverse by a function f, and so on. We'll see why it is important. The most important, I think, is the inverse of a set, and I will show you how easily we can get an algorithm able to compute the inverse of a subpathing or an interval of sets by a nonlinear function f. That is the idea. This set inversion. I will show you how it works. Not so difficult. Oops. Okay. So let me take here Rn, a function f, Rp. I have here a subpathing, or let me take, for instance, for simplicity, I will take a box. This box will be 1, but it can be any subpathing. Here, I have something like this, for instance, it can be f minus 1, the reciprocal image of y. I mean, if I take a point here, I go here. If I take a point outside, I go outside. How can I compute this set? So the idea is to compute this. Then, how will I do it? I will take a box here, for instance. I will compute the image of this box. The image of this box, of course, by f is something which is complicated. But what I am able to do is to compute an enclosure of this one. If this enclosure, so if f of x is included in y, what can I conclude? Here is an unknown set, x, the one I want to characterize. I can conclude that x is included in x. You agree with this? Now, if f of x has an empty intersection with y, what can I conclude? What can I conclude? I can conclude that x is outside. Okay, so it means if I take a box here, and if I am here, I can conclude that this one is outside. Okay? Now, if I take a box here, if I take this, what should I do?
Partition, make it smaller.
Partition.
I will bisect it. Okay? Now, if I take a box here, can I obtain this?
No.
Yes.
Yes or no?
Yes.
Yes, I can.
Yes.
Right.
Because the image of this can be this. And even if I have the minimal inclusion function, I will have to bisect it. Okay? You understand? If I take a box here, if the image is here, but due to the pessimism I intersected, I will have to bisect it. But I know that I will have to bisect, but since it is convergent, at one moment, the ambiguity will disappear. Yes?
You're assuming that F is injected.
It means that?
Is F injected?
Not necessarily. Any F. What is important? F should be continuous, so a composition, even not continuous, a composition of elementary functions. That's all. So, sorry. The algorithm is what I explained. I have two tests. Oh, that's what I explained. It is the Siga algorithm. The Siga algorithm is just the one I have explained. First, I start with a big box.
Can you clarify? In your map, is that the inclusion map of F, or that sort of interaction, or they just because in the Lewis they create inclusion function of F, not the original function? When you sure that is that the original function F or the inclusion?
F is the original function.
function.
Yes, it can be any function.
Okay. Because I see the second part is easy to understand. That part is. But that's why when you the second problem was the complication a little bit. So I thought you were talking about the inclusion function or just the original.
Okay. When this is the inclusion function.
Yes. That's okay.
Yes. Okay. F. So if I take a box, you see the difference.
Yeah.
Okay. So
I saw some of the property expand. It looks like it is the inclusion function property, not the original function property. That's why.
yes, it is an inclusion function property about the inclusion
Yeah,
function.
when you put the F there, strictly speaking, that implies the property is the original function. Hey, forget it. I think I don't want
Okay. Okay. So let me explain you the algorithm. I start with a big box. Big box. I use a stack. So at the beginning, the stack contains only this big box. First, I will compute the image. But the image will be like this, will be huge also. Of course, it will be huge. I will not satisfy the first one because I am not included in Y. I am not outside Y. This box is ambiguous, I have to bisect it. I will put the two on the list. Then I will, so I second, I put the two on the list. The list is not empty, so I come back
to step 2. I take one of them. I bisect, and I will obtain some kind of decomposition like this. The stack will increase, and when the width of X is smaller than epsilon, I will not bisect anymore. I will draw them yellow. Yellow because I will show a picture where it is yellow. When it is inside, I will draw them red. When it's outside, it's blue. So the code of color is like red is the earth, blue is the sea, yellow is the sand. Okay, just to remember the technique, why I have chosen these colors. Okay, so let me show you a small, I will take any function. Option, excuse me, I just have to change the option without contraction. Okay. Okay. Well, okay. You can see how it works. I will explain. First, I start with a big box, and I have here an inequality. So the function f here goes from R2 to R, and to x1, x2, it associates x1 squared plus x2 squared. The set I want to invert is the interval 4, 9. If I take the box, if I am inside, it will be red. If I am outside, it will be blue. Okay? Blue, red. Understand? So, what I wanted to say before, I have a precision here. I can put something, for example, up. You understand the precision, the role of the precision? It is an epsilon. You understand that the whole blocks has been tested outside using interval analysis. I can put also any kind, for instance, sine of x1 plus x2 in, for instance, 0, 4, something like this. I can run. I can take a better precision. For instance, I can inverse sets that are defined by nonlinear inequalities. So, what I want to say is that here, I have an inclusion, I have the function f, which is given here. It has two components, and the box I want to invert is 49 times 04. It is a set inversion problem. Solving equations. For instance, if I want to solve x1 squared plus x2 squared equal to 4, and sinus of x1 plus x2 equal to 1, or to 0, for instance, it's a set inversion problem where what I want to inverse is 4, 0 by this function. So solving nonlinear equation can be seen as a set inversion problem. So if here I put, for instance, 4, and here I put 0, I will obtain a set which is very tiny. So I was able to do something new that was not possible to do without interval analysis. I am able to solve nonlinear equations, non-convex problems, and to find all solutions in a guaranteed way. If I have no solution, I will have a proof that I have no solution. It's important to understand what is new, what we can do that was not possible to do with any Monte Carlo methods or any other method in a guaranteed way. Okay? So of course we can do global optimization and we can deal also with differential equation and so on in a guaranteed way. So just presentation of what interval analysis can do. It's okay? Of course I can do, I stop this. Okay. Inverses of an image, I can compute the image of a subpaving